The first thing that I want to do is I want to formalize this idea of charge transfer, right? So we have in our previous example we had was a piece of wire, and then charge, specifically electrons, would flow through this wire, right? So when these electrons flow through, this is our charge kind of flowing. This right here is what we normally refer to as electricity, electric flow, right? So this here, what we're going to call this is current, right? So this is our electrical current, and very simply to define this, this is just the amount of charge that is flowing through a certain let's say a certain cross section. Like you just put a gate up and just how much charge flows through um, every second. Okay, so this is our charge is just flowing through. This is our current. Okay, so that's pretty much the only thing that we haven't gone to in detail so far. We already have this idea here of Ohm's law that we started using before with resistance and resistivity. We have this formula right here. And basically, everything has some sort of resistance, right, to electrical flow. So if I wanted to flow some current through some resistor, something that has a resistance, I need a certain amount of here is like my electric potential to get it to flow. This is our driver for current, and I need a certain amount based on the amount of current that I want to get through and the resistance of the object I want to get through it, right? So it's a pretty simple formula to work with, and you guys will use this a lot, and um, so you'll have a lot of practice with it. It'll be pretty straightforward to use. So what we're going to do is we're going to now put this together. Remember, we have our resistors. We end up considering this a resistor, right? And I think we used our formula here as V over I. Okay, all I did is I shuffled around this formula here to get my resistor by itself, just so you guys know. So what we're going to do now is we're going to put this in circuits. And there's two ways we can do that. The first way, we'll make a circuit here. This is my battery. The first way I can do it is, remember, if I put this in my circuit right here, then I can use this formula. That's what we did. We have our battery that provides us some voltage, and then we have our resistor that we hooked up. But this time I'm going to make it a little bit simpler since I'm going to be using a lot of these. And I'm going to use this little symbol right here to denote a resistor. Okay? So this is just my symbol for a resistor. When I do this, now I know the amount of current that'll flow through based on how much resistance this has and how much voltage my battery has. Okay. So that's our simple version here. For example, if my resistor was equal to 10 ohms and my battery had 10 volts, right? Just a simple example here. If I wanted to find the amount of current that will flow through, I use my formula, but I have 10 is, this should be I, oops, times 10. So my I will equal to 1 amp, right? So, oh, sorry, this is our new standard unit here, just in case we haven't gone through that before. It's amps. It's just charge over time. Okay. So 1 amp is my current. That's the amount of charge flowing through each second. Okay, so it's pretty simple to use. What we're going to do now is we're going to start to combine this, okay, in two different ways. Because this right here is very, very simple circuit. This is almost nothing. This is like just a light bulb hooked up to a battery, and that's it, right? But most things that we want to build or make or use are going to be much more complex than that, right? So what we need to do is we need to set up some rules for how do you combine these resistors. So let's actually change this. So now I'm going to combine these in one of two ways. I can combine them in series, right? And in this case, let's say I had R1 was 5 ohms and R2 was 2 ohms. Okay, and I want to put both of these in a circuit. There are two ways I can do this. The first way, okay, let me give myself a little more space here. The first way is I can just put them in right next to each other. Oops, that one got a little bit messed up there. I'll just keep them the same color just to make it simple. So now I have two resistors next to each other right here. So we need to find out like what's going to happen when I connect my circuit this way. Okay, so first of all, we need to look at where is the current going to go when it flows through, and then how much resistance is the current going to meet, right? So if current is flowing through, first of all, it only has one path. You can look at it as, as if we hook this up as some sort of water kind of piping. So water would flow through here, and it doesn't have any choice. It has to go all the way around and come back. It has no forks, no anything. It has only this one path. So first of all, whatever current is going through this resistor also has to go through this resistor, right? So that'll be one little rule here. This is for series. Okay, I'm going to put some rules. I1 is equal to I2 is equal to I total, right? Whatever current goes through here has to go through here. The same thing as the currents going through the whole circuit, okay? And then second is when we start, we have a certain voltage right here. And when we end at 0, right? So we have to spend kind of our total voltage from one end of our battery to the other end, right? So that means some voltage is going to be lost here, right? It's going to drop. It's going to have a potential drop because we're going to need to do work, right? We're going to need to do work to get the charge across this. So some potential is going to be dropped here, and then the rest of the potential is going to be dropped here. So we have another rule right here that whatever potential is dropped by the first one plus the second one, it could be plus the third one, whatever, okay, all this holds. All of this together will equal to I total, will equal to my total voltage, right? If I add them all up. Okay, and then the last thing here is how much resistance is there actually in this circuit? Well, if I were to put these really close together, or if we imagine this again as two pieces of wire that I put in my circuit, and then I put them closer and closer together, and closer together. This could be just considered one long piece of wire, right? And when we did our resistivity lab, remember we had this, all I'm doing is I'm combining this length here with this length here. So I'm just adding them together and just making this longer. So I'm increasing this resistance by making it longer, right? So we come here to our last rule here, which is that R1 plus R2 is equal to, I'm going to call this R equivalent. Okay, it's my equivalent resistance. Okay, the reason for this, that why I call it equivalent, is I just need to add up these two resistors together. This one could be 5, this one could be 2, right? This one could be 5 ohms, this one could be 2 ohms. But it's equivalent because if I add them together, they are equal to one resistor that is both of them added together. That means once I add them together, I could draw another circuit that just has one resistor that is 7 ohms, right? I have 5 plus 2. And these two circuits are equivalent. They're the same, right? In terms of the way current flows through them and the voltage that's driving them, all that stuff, they're equivalent to each other. That's why I call it here as equivalence, because I can combine these two into one when I do any calculations on it, right? And this works, you can keep lining up more and more and more, and you can just keep using this rule to add them up together, okay? Does anybody have any questions so far, right? Any questions so far? So really quickly here, what's one of the things that we need to keep in mind when we have elements in series, okay? If I were to remove, okay? If I were to remove this 2 resistor, okay? You can do this if this was like objects that I'm plugging into my circuit, if I just switch it off, right? Or if you think of this as like light bulbs on a circuit, this one is like this light bulb broke. Okay, what happens to the current in this circuit? Try to think about this. So it can't flow, right? It can't flow because my current will come up through here, go through the first resistor, and then here it'll stop. Because now I don't have anything connecting these two ends here. If my resistor is broken, or if I took it off, but I don't connect these two, then my current completely stops. So in here, in series, if you remove one resistor or disconnect it, then the whole thing turns off, right? So you can kind of think of this as like, you guys had those light bulbs, sorry, those Christmas lights that came on a string, you know, maybe the new ones don't really do this, they try to get around this, but you had like the old Christmas lights on a string, and then one of them would go out, the rest of them would go out, right? This is sort of that idea, that they're all hooked up in series, but that means if you take out one, the whole circuit is now open. It can't complete its loop. Okay, so we're going to think about this because this is important when we talk about our other configuration, which is parallel. I can also hook up resistors in parallel. We're going to use the same R1 as 5 ohms and R2 as 2 ohms. Okay, but this time what we're going to do is we're going to use this in my circuit here as a fork. Sorry, take out a little chunk here, a little chunk here. So I'm going to put R1 right here and my R2 right here. So this will be R1, this will be R2. Okay, so I can also plug things in parallel. So I can kind of fork off my circuit and then plug a bunch of things in kind of next to each other instead of in a line. So this is very different because if we think about now the way current can flow, it's not like it was here before where current can only flow one way. Let me go and put this back in. Those are nodes. Okay, it's not where it was before where current can only go this one direction. Now, if it's trying to flow, it could come through R2 right here and come back home. Or it could go through R1 and then go back home and then completely bypass the other one. So one effect of this is that these are resistors, but they don't completely stop current. So this is, you know, you could keep opening up essentially more lanes in the highway. You're right, your current's trying to get from work back home. And then even if you have more resistors here, you have more lanes, so you're still going to get more current flow. So it's weird because I can keep adding more resistors in this way, but my resistance will actually keep slowly going down. It'll go down, 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 instead of going up. Because in each of these cases now, if I add more resistors, my current has more chances to get through, to squeeze through somewhere, right? So the way that we're going to show this in a is this right here. I'll go and write it on the left side here. 1 over my R equivalent, okay, and I'll show you why I'm going to do this in a little bit, is 1 over R1 plus 1 over R2 plus, you know, as many you want, right? So you can do this as many times as you want. So what happens when we actually do this, right? Let me get my calculator out here so I'm ready. But if I had R1 was 5 ohms and R2 was 2 ohms, before when we did this, we combined them and got 7 ohms, right? Now we're going to combine them and see what our equivalent resistance is. So this, if I said 1 over 5 plus 1 over 2, okay, this here is going to be equal to, let me go and do this. This is 7 over 10. Okay. So I have 7 over 10. But remember, this is 1 over this. So I want to flip it over. I want to flip everything over because this is 1 over my equivalent resistance. So I'm going to take both sides to the -1. All that does is flip them over. And I have my equivalent resistance here is 10 over 10. This is equal to, this is about 1.42 ohms. Okay. That means if I combine these two into one resistor the same way I did here, take these two and combine them into one, is when I combine them, their resistance together is 1.42. That's less than 5, less than 2, right? So you can see here that I now have less resistance than I did before by doing this. Okay? Like I said, this is kind of like opening up more lanes on a highway. Even if there's resistance, even if there's potholes in the way, they're going to slow you down. More lanes will allow you to get through a little bit easier. And so that's this idea of parallel. And it has a few things now that are different from our rules for series. So the first thing is that now current can go through this bottom fork or the top fork, but either way, when I add up all the current going through here at the end, it has to be back to my total, right? So I have whatever current goes through the first one plus whatever current goes through the second one this one is equal to my total current. You can see this is already backwards from what we had before. And the other consequence here is that here I start, let's say, at 10 volts. When I go across this first resistor, this is the only thing in my way. So 10 volts, resistor, home, right? So at home, I'm 0 volts. When I start, I'm 10 volts. So when I go across this resistor, I have to drop those entire 10 volts. I have to do that. All my voltage is dropped over that, right? So I have 10 volts here. Or if I go the other way, I still have to drop those 10 volts, right? Remember, I have to spend all my voltage by the time I get back, so I can spend it all here. So in both of these